So it is my pleasure and honor to let you know that we have in this morning another distinguished lecture. Very well-known Italian professor working in Germany at Frankfurt University, head of department, relativistic astrophysics, and the director of the Institute for Theoretical Physics at Goethe University of Frankfurt. Professor Luciano Rezzolla. He has kindly agreed to visit us and to give a series of lectures at this school. Professor Rezzolla completed his undergraduate degree in physics at the University of Bari and University of Trieste. After he received his PhD under the supervision of John Miller from CISA in Italy. He passed through postdoc experience at the University of Illinois and Urbana-Champaign and specializing in black holes and neutron stars, and he returned to CISA then. And finally, he became head of numerical relativity group at the Max Planck Institute for Gravitational Physics in Boston. Alongside his colleagues, Eino Fage and Michael Kramer, he received 14 million euro research grant for black hole research. So, he is also and co-author of a textbook, very well-known textbook, Relativistic Hydrodynamics. It is very pleasure for us to have him here for this school. Please join me to welcome Professor Rezzolla Luciana very warmly.
Thank you, Alikram. And
thank you.
So, welcome everybody. It's always difficult to give a lecture at a school because in contrast to what you have in a classroom, you never know what is the level of the students, and you come from very different backgrounds, very different levels. So the only way to make progress is if you stop me anytime you don't understand something. Don't forget, you are here to learn and to ask questions, and I'm here to try and give these answers to these questions. If we fail, it's bad for both of us. So interrupt me anytime. The rules of the game are I give lectures, you follow. That means no laptops, no cell phones. I think you can do without your email for a couple of hours. And I'll try to give a whiteboard lecture, at least for the first two, because they are a bit more mathematical, but the second two will be a bit more with the beamer. So lecture 1 and 2 will, this morning will be about, so the topic, the topic I'll cover is binary neutron stars. And I'll try to explain there is a lot of things you can do with binary neutron stars. The first two lectures will be about math and how you model neutron star binaries. As you will see in lectures 3 and 4, there is a lot of nice things you can do, but I also would like to impress that this is not something that happens by magic. There is a very solid mathematical theory that allows us to do these calculations. Lecture 3 will be about the physics of neutron stars, what is it we can learn in terms of physics, so gravitational physics, nuclear physics, from binary neutron star mergers, and lecture 4 will be instead on the astrophysics. What is it that we can understand in terms of these as astrophysical objects? Okay? So for lectures 1 and 2, I'd like to suggest a few books. These are Alcubierre, Baumgarten, Shapiro, Goguyon, and then there are a couple of chapters in my book that also covers part of the stuff that I will discuss today. So, let's start going. The equations we want to solve are very well known, and these are the Einstein's equations. So, is everybody able to read what I'm writing? If you can't, then I will use the beamer. But if you can, then we're fine. How many people do not know these equations? Please raise your hands. Okay? So most of you know these are second order partial differential equations that on the left hand side have what is called the Einstein tensor. This is a single tensor which is a measure of the geometry of the system. And on the right hand side there is an energy momentum tensor which tells you about the matter or energy content of the space-time. So this is telling you that geometry is equal to energy. These are the Einstein's equations. In addition to this equation, you want to conserve fields. In particular, you want to conserve matter, and so you need two conservation equations that conserve the relevant quantities that the system has to conserve. So energy, momentum, and mass. And so the first equation is a conservation equation for the mass current. You can also write this as d mu rho u mu, where rho is the rest mass density and u is the flow velocity of the fluid. Okay, so whatever fluid is flowing, if it flows in one direction, has to go and come back in another direction. And then you want to conserve energy and momentum. So is the divergence, the four divergence. This is a four-dimensional covariant derivative of this energy momentum tensor. Okay, so this is conservation of mass, if you want, and this conservation of energy and momentum. This object over here, T mu nu, is a tensor that can be seen as the combination of many different tensors. If you have only a fluid, then this would be just a energy momentum tensor coming from the fluid, and that's easy. But most of the times that's not enough, especially in astrophysics. You need to take into account the fact that it's not just a fluid that is undergoing some motion, but there are also fields, electromagnetic fields or scalar fields. In which case, you will have to add here to this tensor a part which has got to do with the electromagnetic field. If there is a scalar field, you will have something associated with a scalar field, and so on and so forth. Okay, so this energy momentum tensor can be seen as the combination, and what you are asking is the conservation of this total energy momentum tensor. And if you have additional fields, then you will have additional equations that you will have to solve for. So for instance, if you have a electromagnetic field, then you will have a certain Faraday tensor that you need to conserve, and two sets of equations can come from the first two Maxwell equations, and then you will have another equation that tells you about the other two Maxwell equations. Okay, so these are Maxwell equations. And this is the Faraday tensor. This is the energy momentum tensor. For a perfect fluid, this would be given by rho E plus rho u mu u nu, E plus P. This is the energy density, and this is the pressure. And G mu nu is the metric tensor. So I'm trying to give all the names of all the quantities that you see on this board. Let's see if I forgot something. This is the Ricci tensor. Okay, this is what I forgot. Fluid velocity. And this is the density. Okay, so these are the equations that if you want to model binary neutron stars, you have to solve. How do you do this? Well, these are tensor covariant equation. That means they are tensor equations. You can write them in any coordinate system that you wish. You are free to do whatever you want. And Einstein said even something more subtle, that space and time actually do not differ. You can think of time just as a spatial coordinate, so that, you know, thinking of me going to the left or me thinking going in the past or in the future are conceptually and mathematically equivalent. So while this is true and remains true, we have to bear in mind that we have a certain perception of things where time is a preferred direction. Things happen, and our brain thinks in terms of things happening at a given time, in the past, and in the future. Not only that, all of the methods that we know about solving equations that come from mathematical theory, numerical analysis, have the idea or have been developed to solve problems where time is an evolving quantity. And so the idea that people already in the 60s have pushed is you take a given manifold, so this is a given collection of events. You take a metric G, and out of this you go on and do a 3+1 splitting of space-time. So this is an operational choice. Is not dictated by the equations, and in fact you can just say, I don't like this. I would like to have a different representation of the manifold. But this is the way it's much easier for us to do it. And so what we do is we take these manifolds. So you have to think this is a container. Like to think of manifold as a container that contains certain things, and these things are called events. So this is M, and I take M, and then I take a slice of it. Okay, take a slice. I draw it like that. And I have infinite different ways of setting this slice, but the way I choose is that I say that T on this slice, so I have a certain coordinates that I've laid to cover these events, and I say that on this slice, all of the events have the same time coordinate, okay? All events have same time coordinate. And you may say, well, wait a second, what is time? And I say, I don't care. It's one of the 4 coordinates. So I choose this object, and I take a slice where I've chosen the slice in such a way that one coordinate, I call it time, you call it whatever, is the same for all of the events on this. Okay, so that's the first step. I need to use this one now. Once you have a slice, the next thing you want to do is understand where is the future and where is the past. Okay? You just said time here is the same, but I would like to know where is it that time is growing and where is it that time is decreasing. Or where is the future and where is the past. And that's not too difficult to do. So you can think that you define a one norm, which is normally called omega mu, which is just the covariant derivative of the time coordinate. So this one norm is telling you in which direction this coordinate t is growing. And you can think, therefore, that omega mu is oriented like so. Okay? Everywhere on this slice, I can think I can define this one norm omega nu. And this now allows me to define what is, where things are growing or where things are decreasing. In particular, I can define the L2, the norm of this one norm, which is just the contraction of omega, so it would be g mu nu omega nu, and this would be just g mu nu nabla mu t nabla nu t, and this is, I have no reason to believe that this is a constant. Actually, this is a function, and so I call this function minus alpha to the minus 2, so 1 over alpha squared. Okay, and I call this quantity the lapse. For you now, this is just a name. Later on, it will become clear why it has got actually this name. And so it's a way of ordering things. And now I can define another slice of the same type as sigma t, is a different one. But has the same properties. That is, on this slice, everything is as a constant coordinate, and so I call sigma of t plus delta t to indicate that this is different from sigma t. And I can use omega to know whether this new slice is above or below my first slice. Okay? Questions, comments? Something else that I can define, I have a slice, so this is just telling me, this is not a vector, this is a one form. It's just telling me in which direction time coordinate is changing. But because I have a slice, I have a surface, I can define the normal, right? Anytime you have a slice, you have a surface, you can define a normal. So I can define the normal to sigma t, and this normal will be just given by, will be just parallel to the one norm. So it will be g mu nu omega nu, or if you want, minus alpha g mu nu nabla nu of t. And the condition I impose is that, well, this is naturally a time-like vector, right? Why is it naturally a time-like vector? Who can answer this question?
Its contraction is minus 1.
Say it again, say it again.
Its contraction itself is minus 1.
Well, first of all, I haven't even said that. So you cannot give me that as an answer. It is time-like because it is parallel to omega. And omega is a long time, and so must be time-like. Now impose that is unit time-like. So time-like comes from being proportional to omega. Unit comes from the fact that I impose that n mu and mu is equal to minus 1. So I could give this any number I want, but I give it 1, and it's minus because it's a time-like vector. Okay, so now I can draw. Fortunately, I don't have a whole lot of colors I can use that would be compatible. Anywhere on this slice, I can draw a little vector, which is my normal to the slice. And actually, this is very useful. It's a very useful vector because it allows me to define a spatial metric. You see, I was starting from this object M, the manifold, and I was starting with a 4-dimensional metric. But then I started slicing things, and this brings up a new need, a need of defining distances on sigma. So I can define, by the way, something I mentioned to say, all of this is on some lecture notes I will give you out. So you need not write everything, because anyway it's written in the notes. I can define this new tensor, gamma mu nu, which is defined as G mu nu, the one I already know, it's the metric of the manifold, plus a double tensor, a rank 2 tensor given by n mu and nu. And so now I have two important tensors of different ranks, but still two important tensor, gamma, this metric, and the normal n. Why is it that they are important? Well, they are important because out of these two objects, I can build two projectors i.e. two operators that transform a generic tensor, a generic 4-dimensional tensor, into either a fully spatial or a fully time-like tensor. Okay, so the way you do this is you introduce this mixed object, gamma mu nu, which is defined as G mu alpha gamma alpha nu. And so this would be just delta mu nu plus n mu and nu. And you introduce another object, which is this time-like projector. So I'd like to have two rank 2 tensors, gamma and n, with one contravariant and one covariant index. And this I define to be minus n mu and nu. To see how much you have followed, let me ask you this question. What is this? What do I write here? What is the result of that scalar product? 0. 0. Why 0? Well, because these are two orthogonal operators, okay? So the way you have to think about it is that you have your, yes, where is the blue? You have your sigma, your time-like t constant slice. Then you have any object that you want, a tensor which is a full 4-dimensional tensor. I've write it t. And then you have these two operators that allow you to take this tensor and find the projection. So you will have a fully spatial projection, and this would be gamma dot t, okay? I'm acting on t with gamma, or I will have a fully time-like projection, and this will be n dot t, okay? And of course, gamma dot n is equal to 0. Questions, comments? So,
Is it true to say a fully time-like tensor has only one non-zero component around time direction?
well, it could be a higher rank tensor, and so it might have more components. But what you said is right. A time-like tensor has all the spatial components equal to 0, and only the time components non-zero, and vice versa. A fully spatial tensor has only spatial components non-zero. So, although in the future I might still consider this to be a four-dimensional tensor. For notation, I will give I could call this guy R, okay, and I could still give Greek indices to this guy, because it's convenient when I project it. But this object, you have to think, is an object where a part of it is 0 and then the other part is non-zero, and the same here, okay? So for notation, I can still consider this to be a fully four-dimensional object, but I know that a part of it is 0. That was a good point. So, question, what do we use G for in this manifold? What is useful? Why is this an important tensor? What is the metric there for?
Because it describes the geometry of the four dimension.
Okay, it's a bit vague as an answer, Serkan. Describes the geometry. A bit more precise. Right, that's the second. The second definition is the one I need. It defines the distance between events. So I take two events in this manifold, A and B, wherever they are placed, and may ask what is their distance, and their distance, ds squared, will be just g mu nu dx mu dx nu. Okay, so it gives me a distance. G gives me a distance in m. Then you can understand that gamma gives me a distance on sigma. Okay? So just like G gives a distance in four-dimensional manifold M, gamma gives a distance on three-dimensional sigma t. So I haven't remarked this because I think it's self-explanatory. By the time I take a slice, my slice is three-dimensional because I've cut out one dimension. Okay? So if I now want to know the distance between 2 points on sigma t, okay, say these 2 points over here, I want to know how far apart they are, I need not use G, I can just use gamma. Okay, so one point that we have to clarify is, we want to go from these equations, G mu nu nu equal 8 pi T mu nu, to a 3+1 version of those equations. And if you remember, there is an operator which is essential in defining the energy, the Einstein tensor, and then the Riemann tensor and the Ricci tensor, which is the covariant derivative. Okay, what you have here, if you dig down, deep down, you have that these are just covariant derivatives. So what we need now is a covariant derivative of. We need equivalent of covariant derivative on sigma t. And I know how to calculate the covariant derivative, say I know how to calculate nabla rho of a given tensor T sigma tau, okay? And I would like to have the equivalent, so this is in 4D, and I would like to have the equivalent, which I call D, little d, well, capital D, but not a nabla, of this new tensor T. Let me say that I want this to be called T alpha beta delta. How do I go from this object that I think you all know how to compute, okay, over to this object? Suggestions are taken. Yes?
You can decompose a metric.
Okay.
Space then time by parts.
Yes?
Then we can write operators.
Yeah, but you don't need to do that because you have already introduced these two objects. So all you have to do, and this is why it's nice, is use one of these two objects. Which one do you have to use?
Spatial part gamma.
Gamma. Okay, so all you have to do here is put in 3 gammas. Voila. And then you have to get the indices right, okay? So you get an alpha here, you get a delta, a sigma and a delta, and here you have a tau, a beta, and a rho, okay? So now this is the spatial equivalent of the covariant derivative. So you've taken the covariant derivative, and you have contracted each of the index with this operator over here. Okay, so, and you will not be surprised to find out that if you do all of the just like this was true, that the the metric has 0 divergence, you will find out that d mu of gamma mu nu is 0 now. Okay, so the way we say is that the covariant derivative is compatible with the metric, the 4 metric. This is the 3 covariant derivative is compatible with the 3 metric. Okay, I don't write this because it would take too long. Okay, let me erase here. Okay, so how do I use the fact that I've introduced the basic differential operator, the covariant derivative? I can just go back to what I know in 4-dimensional relativity, where I start with g mu nu, which I know comes from r mu nu, which I know comes from, actually I should do the other way around, right? Which I know comes from the Riemann tensor, which I know comes from the the Christoffel symbols, and which I know come from the covariant derivative. Okay? So if you remember, the way you've studied general relativity and ended up with the Einstein tensor is you introduce the covariant derivative, the Christoffel symbols. These were used to define the Riemann tensor, then the Ricci tensor, and then the Einstein tensor. So we do have to follow the same logic here, and we have now to this new operator, which is d mu, out of which we will get a gamma mu nu gamma alpha beta. Is just to remind myself that this is not, that just like this is a 3-dimensional operator, and I have used a different letter to remind me. Here I cannot use a different letter, I will be confused, so I'll put a little index here, 3. So this is to remind that this is really an object living on sigma, out of which I build a 3 version of the curvature, of the Riemann curvature. R mu nu alpha beta, out of which I build a 3 version of the Ricci tensor, out of which I build a 3 version of the Einstein tensor. Okay, I hope you are still all following. So, how do I define these objects? Well, it's very easy. I just have to use exactly the same definition that I used when I was defining these objects in a 4-dimensional space. So, gamma 3 alpha beta delta is equal to 1/2. So, yeah, let me start with the 4-dimensional, okay? This would be G alpha mu, and then I have here 3 spatial derivative. You know, everybody has his own mnemonic way of computing this. Mine is that I take the d mu of G beta delta. So I take the last 2 indices for the last object, I put a minus sign, and then I permute. So I would have delta G mu beta, and I would have here d beta G delta mu. And you can have now the same object in a 3-dimensional slice. Gamma 3 beta delta will be exactly the same as this guy, where I simply replace G with gamma. So I have alpha mu, and I have d beta gamma delta mu plus d delta gamma mu beta minus d mu gamma beta delta. So I've done the very first step of my construction. I have defined the spatial covariant derivative, and out of the spatial covariant derivative, I've defined the Christopher's impulse. I would like to calculate this guy over here. Does anyone remember how you calculate that object in full 4-dimensional? Yes? It's not just a double covariant derivative, it's the antisymmetric double covariant derivative, right? You have to take first in one direction, then in another direction, then compare, okay? So if you remember, taking a vector field W, mu, and taking the twice the covariant antisymmetric derivative, say alpha beta of this object, W delta, this would give you a right-hand side which is either 0, or if it is non-zero, is proportional to the alpha beta W mu, okay? So for those who are not familiar, who don't remember this, the idea is that you take a vector field, W, and you first move it in one direction, and then in another direction. Let's say you make a path in a clockwise manner, and you, after the pilot transport, this would be your new vector, and you do the same on an antisymmetric path, so say in a counterclockwise direction, and then you have a new object, W prime, and you look at the difference between these two, and if this is a difference, this is embodied by this tensor. If it is not, if there is no difference, as you would expect in flat spacetime, then you say that the curvature is 0. So we do exactly the same here, but with this new differential operator, which we've just introduced. So it's do twice d alpha beta W delta is equal to R3 mu delta alpha beta W mu, okay? And, well, you know, this object has the obvious properties that it is fully spatial. So if I take this object mu alpha beta delta and I contract it with the normal vector to the slice, what do I get here? Sorry?
The time-like part of the
No, I don't get the time light. 0. Because this is already fully spatial. Okay? And, okay, just for notation, for those of you who are not familiar with these square brackets, if I have a tensor and I have the indices between two square brackets, I'm just saying this is the combination of T alpha beta minus T beta alpha. And so in exactly the same manner, you can calculate, so these are fully spatial, and I will not go into the details, but you will see that R3, R alpha, beta, gamma, delta will be a function of what? In 4D, this is a function of what?
Metric and Christoffel symbols.
Yes, well, a metric is in the Christoffel symbol, so just concentrate on Christoffel symbols.
Christoffel symbols to the derivative of Christoffel.
So it's Christoffel symbol squared, okay? Let me call it gamma squared, okay? So this is the 4-dimensional object, gamma squared, and as you said correctly, it's the second derivative of the Christoffel symbols. Sorry, is the first derivative of the Christoffel symbols, okay? And if you look at the dimensions of this object, the Christoffel symbol is a derivative of the metric, and so it's 1 over a length. So this is 1 over length squared. This is the derivative of a Christoffel symbol. So this goes like a length to the minus 2. And so this is a curvature. It's the inverse of the curvature radius, or the square of the curvature radius. And you can do exactly the same here. I will not do it. All I'll do is, because I'm lazy, I'll just put in a 3. Okay? So I can work out what is the 3 Riemann tensor, and this will be just a combination of the 3 Christoffel symbols on sigma t. And once I have this guy, I can calculate the 3 Ricci. Do you remember how you calculate the Ricci in general relativity, in 4-dimensional general relativity? Say alpha beta. This would be the contraction of the first and third index. Okay. And I do exactly the same here. Okay. Out of R3, I get the Ricci tensor, and out of the Ricci tensor and its contraction, I will get the 3 Ricci scalar, which is therefore the contraction of the Ricci tensor. Okay, so we should not lose track of what it is that we're doing, okay? We're trying to, essentially what we're doing is we're doing differential geometry in a 3+1 splitting. It has taken us a lot of time to learn differential geometry in a 4-dimensional manifold, space-time, and now what I've done is I've broken up that, or I've recycled that notion to do differential geometry in a subspace, this 3-dimensional subspace. Is it clear so far? Are there questions? Yes?
I didn't quite understand the W vector. Is that a vector or vector field? I didn't understand.
It doesn't really matter whether it is a vector or vector field. So for all practical purposes, you can think in this sketch is a vector, a single vector, but you can think it's in more general footings, it's a vector field. Okay? And what you do is, don't forget that the covariant derivative of a vector field is the parallel transport. Okay? And this is a very lazy way of writing. I'm writing nabla alpha nabla beta of W delta minus minus nabla beta nabla alpha of W delta. And the first part I can think is I'm taking the derivative in a given direction, the one given by alpha. You know, you can introduce a vector field in the direction alpha. And so I first take along alpha and then along beta. Actually, the other way around, okay? In this case, I first take along beta and then alpha. And then I subtract to this. This is what I was doing over here, is the subtraction operation of what I would have obtained if I had gone the other way. First in one direction and the other. Now, in partial derivatives commute, covariant derivatives do not commute in a curved space-time. And this is then measured. So if this is non-zero and you want to know, well, how large it is, this is embodied in this object R. And I've done just the same because now I've introduced this simpler, well, this operator on sigma, and I can do exactly the same logic. So instead of thinking of doing a parallel transport in a four-dimensional space, you are really doing a parallel transport on sigma. Other questions? Okay, so there is one point that I was hoping you would ask me for, but you haven't, so I will have to ask you. What the heck is the difference between this object and this object? Well, you can say, well, this has, some of these components are zero, right? Because I'm looking at it just on a slice. Which means that this object has more information than this object, okay? So this tensor has some components that are identically zero, all the time related. And this means that this object has more information than R3. Okay, so I think we all agree this is a fact. Now we have to try and understand what is this additional information that we're missing. And in order to understand what is that we are missing, maybe we understand better what is this R. Again, I have my a space-like T constant slice, sigma T. And this is measuring curvature on this slice, okay? R3 measures intrinsic curvature on sigma T. So I can think I have developed an app which allows me to go around in this room and measure locally this quantity. It's not actually very difficult to do this app. You will find it's almost zero, so that's why people don't use it. But you can build an app that measures locally the intrinsic curvature here in this room, or in the next room. So this is telling us about the intrinsic curvature in this room, but we have no idea about the way this surface is oriented or bent with respect to the manifold, the four-dimensional manifold, because we have no measure of this four-dimensional, this additional dimension, okay? So we need, so the missing information is on how is sigma T bent with respect to M, to the manifold. Okay? We have no idea because all the information that we have is the information on sigma. Okay? It's like imagining you are a two-dimensional object and you're moving on a two-dimensional surface. You have no idea what the surface, the topology of the surface. No? Okay? Is this clear? So what we need is a measure of the extrinsic curvature, what is called extrinsic curvature. And if you want, the extrinsic curvature is exactly the piece of information that was contained in this object and is missing in this object. Okay, so how do we calculate the extrinsic curvature of a surface? Any suggestion on how to do this?
Can you use the projection operator? Backward. As we use the gamma, we have another operator for the n.
What is that you project?
Next slice.
I don't know anything about next slice. I don't care about the next slice. All I have is one slice, sigma t. And all the information I have to use is on sigma t. So I take a cut of this so that I have, this is my sigma t, okay? And I want to measure all of this nice smooth bending that I've shown you here. How would you do this?
Transport a normal vector.
Right, don't forget, you still have a normal vector. So you have a normal vector over here. And you have, because it is a vector field, you have another normal vector over here. Actually, they've done it wrong. Well, the normal vector there would be here, let's say. So this would be the normal vector n at p. This would be the normal vector n prime at p prime. And then I can think of taking n, parallel transporting over here, and this would be n tilde. And what do I do then? I need to calculate the difference, this difference over here. Okay, so this will be delta n. And what else do I need to do? I need to project. I need to make sure that this object is a fully spatial object, because what I want is an extrinsic curvature on sigma t. And so what I do is I just take what I can say is that I will have a tensor, rank 2 tensor, K, which will go like the projection of delta n. If you want to be a bit more mathematically correct, what you define is that kappa mu nu is defined as minus gamma lambda mu, the 3 covariant derivative of the normal vector. Okay? So this is called the extrinsic curvature. And the mathematical understanding comes from here. It's just telling you about the bending, and the way you measure it is you take the normal vector, you parallel transport, that's why we have a covariant derivative, then you project it so that you have a fully spatial object, okay? This is a fully spatial object. Okay? So you can think, in a very loose manner that R mu alpha beta nu is like the 3 R mu alpha beta nu plus the covariant plus the extrinsic curvature. When you put these together, you have all the information that was in this tensor now is in these two tensors. Why do I need a rank 2 tensor? Why not just one? I mean, all I need to do is covariant derivative along one direction. You do need a rank 2 tensor because the extrinsic curvature might be, the covariant derivative might be 0 in one direction but non-zero in another direction. I know this sounds like crazy. Think about a plane, okay, this sheet. This sheet has 0 extrinsic curvature. I take any normal vector and move it around, will always be the same after parallel transport. imagine now you have a cylinder, okay? It's the same as a plane. If I take the normal vector and I move it along the z direction, say, there would be zero extrinsic curvature. But if I move it in this direction, then I would see that the vector changes. It's pointing in different positions, okay? So you might have it then on a surface, the extrinsic curvature in one direction is zero, while it is not in another. And that's why you need two indices in your vector, in your tensor. So let me go back to the example. The intrinsic curvature of a sheet of paper here is what? Is zero. It's flat. And so is the extrinsic curvature. The intrinsic curvature of a cylinder is what? Zero, because it's the same, I haven't done anything special. But the extrinsic curvature is non-zero. Take a sphere, two spheres. Then the intrinsic and the extrinsic curvature in that case are both non-zero. Okay? So these are really independent measurements that you have to bear in mind. There are other ways in which you can define the extrinsic curvature, but you will find them in the notes. I will not go into the details. Okay, so much with that. Where was I? I'm there. Questions, comments? Oh, because it's you know, who's asked this? I would fail any student who puts an equal sign. I mean, look at this object. This has 40, these indices, these are just 2. Okay? It's just a conceptual, you know, equivalence, not a mathematical equivalence. They are really different objects. Okay, so yes.
The cylinder example is single-dimensional hypersurface. In three-dimensional, on a three-dimensional surface, don't I have another dimension?
Yes, in a three-dimensional, you certainly would have a. Sorry, I don't understand what is the question. So.
Because you see, we have two components of K mu, because I can move one direction or another direction. But in a three-dimensional surface, I can move.
No, okay. You still have to think about, you know, the two indices will give you all the information that you need. It's not that because you are in 3D, then you need a rank 3 tensor. That's what you're trying to say. Yeah, no. The number of indices has got nothing to do with the dimensionality.
Yeah.
Okay? Just like, you know, the
But I mean, the example you gave.
you're just going in the wrong direction, okay? Think about Riemann tensor. In 4D or in ND is exactly the same formula. The only thing that changes is the, you know, the components of the indices.
Yes.
Okay? And it's the same here.
Well, I mean.
No. I'm saying you're going the wrong direction. Don't insist on that. We can discuss about this. Okay, so Alikam, what do we do? We have a break or? Okay, so let's break for 5 minutes or so. 10 minutes. Okay, so I'll see you in 10 minutes.